Howdy everyone, welcome back for Chapter 10 example problems, where we're going to take a look at some gas laws, specifically the ideal gas law, the combined gas law, and then how you would use gases in a stoichiometry equation. And so there are other question types, but they tend to be a little more straightforward. This is one where for these I think it's good to take a little time and go through an example. So the first one is from 1043 in the book. It says, suppose a sample of chlorine gas is 8.70 liters at 895 torr and 24 degrees Celsius, and they want to know how many grams of chlorine are in the sample. Well, our clue here is that it's not a before and after question. They're not saying that some change is happening. They're saying at this moment in time, we want to know something about the gas, and that's a clue that we're going to use the ideal gas law. So we're going to want PV equals nRT. But we say, well, wait a minute, we want grams, and grams isn't in here, but we do have moles. And if we have moles, then we can use the stuff we learned way back in Chapter 3 to go from moles to grams with the molar mass of chlorine gas. So that's what we'll do. We're going to solve for N and then change that to grams at the end. So that means, okay, we want moles is equal to pressure times volume over RT. So now we check its ideal gas law. Do we have everything how we want it? Well, first off, temperature, we know for gas laws always has to be Kelvin. So right away we can say, okay, this number we need to make Kelvin. We're going to go ahead and add 273 to that. So that'll be 297 Kelvin. So there's the number we'll use there. The other one is for R, we're supposed to use ATM for pressure. Now there is in your book a value for R, I think it's 62.36, where you can use torr instead. So if you say, hey, I could just look up the other number, great, use it. And that is on your equation sheet that you get for tests, so you could use that. But the one, we'll just kind of practice because most people are more comfortable doing it. We want ATM. So first we're going to set up a little conversion that says if we have 895 torr, and we want to make that ATM, then torr goes on the bottom, ATM goes on the top, and we know from our definitions that 1 ATM is equivalent to 760 torr. So 895 divided by 760, we get this is 1.18 ATM. And now we can plug that in. So now everything's good. The volume is in liters. R is a constant. We're ready to solve for moles. So we'll have that the moles are equal to the pressure, 1.18 ATM, times the volume, 8.70 liters. All right, divided by R, so 0.08206 liter ATM over mole Kelvin, and then times divided by the temperature, so 297 Kelvin. And if we look, right, Kelvins cross out, liters cross out, ATMs cross out, we're just left with moles, what we want. And so we punch this in, 1.18 times 8.70 divided by 0.08206 and divided by 297, and we get, three sig figs, 0.421 moles of chlorine gas. But to get the answer, we want grams. So that means we'll take that answer, 0.421 moles. Moles goes on the bottom, grams up top. Remember, it's diatomic Cl2. So that means it's going to be 70.90 grams. So that times 70.9. I didn't actually round my answer, so it might be slightly off, but we should be good. I got 29.9 grams of chlorine, and that is the right answer. Okay. Oops, sorry. So again, because the sample wasn't changing, we said use the ideal gas law. In this case, because we want grams, solve for moles, and then once we get moles, convert to grams. All right, for the next one, it's part B of the same problem, but it says this time, instead of figuring out how much chlorine, it says what volume will the chlorine occupy at STP. And so here we're changing it. We have a volume and a pressure and a temperature, and we're changing the temperature and pressure. That's our clue to not use the ideal gas law, but instead to use the combined gas law. So P1 times V1 over T1 equals P2 times V2 over T2. Now again, we have to make sure temperature's in Kelvin, so this is still 297 Kelvin, so we're good there. But we're going to leave this as torr, because with the combined gas law, as long as the pressures are in the same units, they're going to cross out. It doesn't matter. So for me, it's easier for STP to say, oh, this is 273.15 Kelvin, and because we have torr, oh, okay, that's just the 760 torr that we used before. And I'll just use those two numbers. So if we plug that in, P1, 895 torr, times V1, which was the 8.70 liters, divided by T1, 297 Kelvin. That is going to equal P2, so that's 760 torr. V2 is what we're solving for. And then T2 is the 273.15 Kelvin. Now to solve for V2, right, the 760 is going to cross down, the 273 is going to cross up. So we'll take 895, just also cross out units while we're thinking about it, Kelvin. So 895 times 8.70, and then times the 273.15 crossing over. Now we'll divide by the 297 Kelvin, and we'll divide by the 760 crossing over, and we'll get that V2 is equal to 9.42 liters. And that answer seems reasonable. It's a little bit larger, but we drop the pressure, and when you drop the pressure, volumes get bigger. Now we also drop the temperature, but it looks like we drop the pressure more, so that factor should win out. If we drop the pressure more, the volume should get larger, and it did. All right, so that's the rest of 1043. But again, we saw the change. We started here, and then we changed the conditions. That means use the combined gas law. All right, last one is our stoichiometry problem, where it says we're looking at cellular respiration. We're combusting glucose. And they want to know what volume of carbon dioxide is produced at 37 Celsius, so human body temperature, at 0.97 atm if 24.5 grams of glucose is metabolized. And so we're going to say, okay, we start with the grams of glucose. And I'll just put like glucose down there. We're going to go to moles of glucose. We're then going to go to moles of CO2. And then from there, we're going to go to the volume of CO2. So there's our kind of plan. Now these first two steps, that's normal stoichiometry. That's our normal dimensional analysis. Just, hey, how many grams per mole, or what's the mole to mole ratio? We can do that. The third step, because we're going from moles to volume, moles to liters, and it's not at STP, so we can't assume the 22.4 liters per mole, that means we're going to need to use the ideal gas law. But these first two, let's go ahead and do them. All right, so glucose, 24.5 grams of glucose. So grams of glucose on the bottom and moles of glucose on top. Now, I happen to know from an earlier problem that glucose is 180.18 grams per mole, or at least roughly if you're using a 2 decimal point periodic table. We'll then go ahead and say, okay, well that means moles of glucose on the bottom and moles of CO2 up top. Here we use our molar ratio. It's 1 mole of glucose with 6 moles of CO2. And then we're going to stop here. We're just going to put equals here, because that third step we said we got to use the ideal gas law. So with this, just these first two steps, 24.5 grams divided by 180.18. So Sorry, my calculator's display is acting up. Then times 6. So this is 3 sig figs, 816 moles of CO2. Right? And now we'll use the ideal gas law that, okay, we have PV equals nRT. We're trying to solve for volume. So that means we'll make that volume is nRT over P. So now we just plug that in. Moles we just got, it's 0.816 moles. R, 0.08206 liter ATM over mole Kelvin. The temperature, okay, we got to change that to Kelvin. Forgot to do that ahead of time. So 273 plus 37, that should be 310 Kelvin. There you carry the 1, yeah. And then pressure on the bottom, it was already in ATM, so we don't need to convert that. 0.970 ATM. And so we'll just punch all these numbers in. So 0.816 times 0.08206 times 310, and then divide it by 0.970, and we get an answer of 21.4 liters of carbon dioxide, and that seems reasonable. It was about 1 mole of gas, so it's about 22.4 liters, a little bit different because of the temperature and pressure changes. But no, all those answers seem very reasonable for what we got here. All right, so I hope these videos helped you. I hope that if you have other questions, come see me, come email me, see the tutors. But I hope that the semester has treated you well and that I see many of you again in Chem 106. Thank you very much. Have a wonderful day.